The insulated gate bipolar transistor, or IGBT, is one of the most important components in modern power electronics. In this video, I'll break down its IV characteristics, how the current and voltage vary, without using complex graphs. Let's start with the output characteristics. That is, how the collector current varies with collector to emitter voltage for different gate voltages. When the gate emitter voltage, or VGE, is below the threshold, typically between 4 to 6 volts, the IGBT remains off. There's practically no current flowing through the collector, only a tiny leakage. But as VGE rises above that threshold, the IGBT starts conducting. First, electrons form a conduction channel through the MOSFET structure. This action then triggers the bipolar conduction mode, where holes are injected from the collector region into the drift layer. At this point, even a small increase in the collector-emitter voltage causes a sharp rise in the collector current. This is known as the active conduction mode. Eventually, as VCE continues to increase, the collector current levels out and becomes relatively stable. This marks the saturation region, where the IGBT behaves like a fully turned-on switch. If I increase the gate voltage further, say from 10 to 15 volts, the IGBT allows even more collector current to flow at the same VCE. That's because the conduction channel becomes wider and internal resistance decreases. Now let's look at transfer characteristics. How the collector current changes with gate emitter voltage at a constant collector emitter voltage. At a fixed VCE, say 15 volts, when VGE is still below threshold, the device remains off. But once VGE crosses the threshold, collector current begins to rise, and it does so rapidly. This is due to the formation of the conducting channel and the injection of carriers. As VGE increases further, the channel widens, internal resistance drops, and collector current increases significantly. The relationship is non-linear, it rises fast. In summary, the IGBT starts off acting like a MOSFET, voltage-controlled and high impedance at the gate. But once it's on, it behaves like a BJT, carrying large currents through bipolar injection. That hybrid nature is what makes it so powerful in inverters, converters, and motor controllers. Thanks for watching. Want to see how IGBTs switch on and off in real circuits? Check out my next video on IGBT switching characteristics. Don't forget to like, share, and subscribe.